Hi folks, my name is Dave Wilson with Texas Instruments, and I'm back once again to talk about InstaSPIN-BLDC. Now, as the name implies, InstaSPIN-BLDC is a new technology for use with brushless DC motors. And to say that it's a new technology is perhaps somewhat of a misnomer, since the technique itself has been around for quite a few years. It's a technique based upon back EMF integration to be able to time when you need to commutate a brushless DC motor. And what we've done at Texas Instruments is we've taken this technology and we've repackaged it into a nice, easy-to-use format. And I have to say that in all the years that I've been doing motor control, I can't recall any other motor control technique that is as robust and as easy to use as InstaSPIN-BLDC is. So what we'd like to do in this particular video is walk you through a step-by-step procedure on how to get InstaSPIN-BLDC up and running on one of our 8312 boards. So grab your board, grab a motor, and let's see if we can get your motor spinning.
So let's take a look at your 8312 board and make sure that it's set up correctly. Toward the center of the board there are two switches, Reset B and Reset C. Both need to be in the center or MCU position. Also, jumper JP1 needs to be in the VR1 position. And then if you go directly beneath that toward the bottom edge of the board, Reset A also needs to be in the center MCU position, and jumper M1 needs to be in the H position. Now let's take a look at the 28035 control card. We're going to have to reflash the program that's in the memory of this part. So what we got to do is make sure that SW3 is in the down position as shown here in order to be able to flash the device. Now let's hook your motor up to the 8312 control card. On the right hand edge of the board there's a 4-terminal connector, and you want to use MOA through MOC. It really doesn't matter what order you put the wires in, because that'll just determine which direction the motor spins. Just make sure you don't hook into the ground terminal, which I've actually done before. I'm actually using a different motor than the one that came in the 8312 kit. First of all, this motor has 14 poles, so it's actually easier for a video to see it spinning when we activate it. Plus the fact that it makes a very satisfying growl sound when it runs. I think it sounds kind of like a diesel engine. Let's go ahead and insert the control card in the DIMM slot on the 8312 board now. And let's see if I can do this with one hand here. It's keyed, so you can't put it in backwards, so don't worry about that. But in the correct positioning, the component should be facing you as shown here. Using the 24-volt power supply that came with the kit, go ahead and connect that up to the power connector on the right-hand side of the board. And if power is turned on, you should see the PVDD LED light up, as well as the 12-volt and 5-volt LEDs. Now let's go ahead and connect up the control card to your computer using the supplied USB cable in the kit. And again, I'm trying to do all this with one hand here. Once it's connected correctly, you should hear the USB connection sound from your computer, and LED 4 on the control card should light up. Now we need to load the InstaSPIN-BLDC code into the flash of the 28035. So I'm going to launch Code Composer Studio version 4. If you get this workspace message, just select the default. Click OK, and this will launch Code Composer. Now under the Target tab, select New Target Configuration. And I'm going to use the shared location so that it shows up in my list of other target configurations. And you can name this file whatever you want it to be. I'm going to select 8312 InstaSPIN-BLDC, and then when you're done, click Finish. Okay. And now we need to configure, we need to set up that particular configuration, and here's the tab that I need to do that with. So I need to open this up. Here we go. And under Connection, select USB version 1 emulator and the 28035 under Device, and click Save. We're going to need to locate this file under the Target Configurations tab. If you don't already have that open, you need to click View, Target Configurations. Now under that tab, go under User Defined and you should see the target configuration that you just created. Right-click on that and say Launch Selected Configuration. Now, under Target, select Connect Target. If everything goes correctly, you should see the little play icon at the top of the menu bar there light up, as shown here. Now we need to locate the program that we want to download into the 28035. So under Target, select Load Program. I'm going to use Control Suite's location. Assuming you haven't changed the default settings on Control Suite, it's on the C drive under TI, Control Suite, Development Kits, and then the C2 Kit version 123 under GUI, and then you want to use the v100.out file right here. Now this is going to take this program now and burn this into Flash. You may also have this file on a memory stick that came with your kit, but we strongly recommend that you use Control Suite to get this file, since Control Suite is updated very frequently and you're sure to get the latest revision. Now you can see at the bottom of the screen here it's actually erasing the flash inside the 28035, and now it's loading the program, and you can follow the progress with the green bar to see how far we have to go. So this might take just a little bit of time, but be patient, and it'll eventually burn the program into Flash. There we go. Now click the red Terminate All button up at the top. There we go. And close Code Composer Studio, and that's it. We've now got the program burned into Flash of the 28035. Before we launch the GUI executable, we now need to remove power from the 8312 board and remove the USB connector from the 28035 control card. Then we need to power it back up in this sequence. First of all, plug power in, and then once that's done, reconnect the USB cable to the control card. Now if the program has been loaded correctly, what you'll see is on the right hand side of the board, the red LED should be flashing now. Now let's locate the GUI executable, and once again I'm going to use the Control Suite location under C, TI, Control Suite, Development Kits, and then C2 Kit version 123, GUI, and then now I want to use the v100.exe file. This is the actual executable for the GUI. And again, you might have this file on a memory stick that came with your kit, but please use Control Suite to get this file. That way you're ensured to get the latest and greatest file for this application. So here's what it looks like. This is actually now the GUI interface that will control InstaSPIN-BLDC. Notice the lights down at the bottom and also the DC bus interface bar. These should all be lit green if everything is connected correctly.
So to make my motor spin, in most cases all I have to do is go down to the bottom of the GUI interface screen and click the Enable Motor button. So let's try that. And sure enough, if we pan over to my motor, you can see that it is indeed spinning. Now, if your motor doesn't start up, the most likely reason for that is because the flux threshold is set to an incorrect value for that particular motor. And you can tune that by just sliding this slider to different values, and we'll show you how to tune your motor in just a minute. But I happen to know that for this motor, it wants to have a higher threshold, somewhere right around 4. So let me slide that over here. And you can see that that does in fact change the sound that the motor is generating. So let's go through and look at the various controls on this GUI interface and see how they work.
So let's take a look at some of the indicators along the bottom side of the GUI interface here. Let's start over here in the lower right hand corner. This is the driver over temperature warning, and this comes directly from the 8312 chip itself. So if the temperature inside the device exceeds 130 degrees C, this light will go red and shut down the operation of the chip. So you have an indication that something is wrong there with the temperature. Your bus voltage meter, you see right now we're actually live, about 24.4 volts, which is within the accepted range. As long as your voltage is within the range of acceptability, this will be green. If it goes yellow, that means you've got an undervoltage condition, or if it goes red, that means you've had an overvoltage condition. The fault status indicator, this also comes directly from the 8312 chip and indicates that there has been a fault which has occurred, most likely an overcurrent fault, and this is a fault that you can actually reset. So if you do see this fault, make sure you disable the motor and then hit reset fault, and you can bring the chip back online by doing that. The control mode selector right here, let's take a look at some of the different control modes that we can use. Right now the default mode is duty cycle. That means when we first power up, all we're doing is really controlling the duty cycle of the motor, of the PWMs. There really is no control loop associated with it. But you can also activate different control loops. One would be a current mode control loop if you have torque control that you want to do. Also velocity control loop. It's a PI control loop for velocity control. And finally, a cascaded control loop. We'll talk a little bit about that in the future. That basically is a cascaded current loop inside of a velocity loop. So you can actually get the best of both worlds with a cascaded loop. Moving on up to the top here, this is the control knob, which is kind of the centerpiece of the whole GUI interface. Depending on what mode you have selected, like in this case if I've selected duty cycle, that means that when I turn this knob right here, it just changes the duty cycle to the motor. So let's go ahead and fire that up, and you can see now as I change the position of the knob, all it's going to do is change my duty cycle from 30% to, in this case, roughly 80%. And you can actually see the motor responding to that. So let me disable it. One more meter I want to talk about. That's the RPM meter up here. And this is actually linked to a control on the second page, the settings page, and it's related to how many poles that your motor has. Now the motor that I'm using here is actually kind of a funny motor. It has actually 14 poles, which is not one of the ones that's listed here. So I really don't use this, but if you want to get an accurate readout of your RPMs, you need to make sure that this is set to the correct value. The default value is 8 poles, and that is the value of the motor that comes in the 8312 kit. So as long as you don't change this, you should have a good readout here for the RPMs. So let's go ahead and fire this back up again. I want to show you that in duty cycle mode, when we start off right here, we can actually see the speed of the motor right here in this bottom plot panel, and I can change that speed, increase it, and you can watch the increase of the speed in the plot panel. And I can actually get it to go pretty slow. Actually, I'm pretty impressed with how slow we can get this motor to go in sensorless mode. Let's take it down to, I think I can get it down to about 0.02. That's a 2% duty cycle, folks. And you can see that the motor will still spin. I don't know what the RPM is, but you can see from the picture it's moving pretty slow. What's even more amazing about it is if you stop the motor, that it will still, when you start it up again, it'll come back. So this algorithm does work down to very, very low speeds, very, very low RPMs. If you want to reverse the speed of the motor, then you want to apply negative duty cycles. That's the way that this convention is set up. So I can just move over to here, and you can see I can make the motor go backwards, very slow in the backwards direction if I want, make it go forward. Again, that's the options that we have. Now, let's talk a little bit about flux tuning, because this is a very critical piece to how your motor is going to operate. And I already mentioned that I knew that this particular motor wants to be set to a flux threshold of about 4. How did I know that? How do we go about the process of tuning this? Well, in order to do that, let's activate some other waveforms here. And you can do that by coming up to the continuous reading button. I'll go ahead and click that. And now we should see some other waveforms that start to appear up here. And let me give it just a little bit more speed. There we go. And I can change the scale factor, kind of like changing the horizontal sweep of your oscilloscope by this number right here. So here we're looking at three different waveforms. The top waveform is the flux waveform. This is the integrated back EMF voltage waveform, of course, which represents flux. And then the green waveform right below that, that is the back EMF waveform. And then this is the current waveform. Actually, when the motor is unloaded, the current waveform looks kind of weird like this. Now, when I load the motor down, you'll see that the waveform will take on a different shape. There we go, kind of that square wave looking shape. And that's what you would expect. But getting back to our question at hand, how do we tune the flux so that we know that we're commutating at the right time? The answer is we want to look at the, well, in this case right here, let's just look at the rising edge of the back EMF waveform. See this right here? Notice it comes up and then just flat tops right over. Here's another good example. It just comes right up and flat tops over. What happens if you're tuned too late or too early? Well, let's take a look at the example first where we're tuned too late. In other words, we set the flux threshold way high, and that means that we're going to be commutating too late. Now let's look at the back EMF waveform and see if we can see a difference in it. Ah, yes. See that overshoot right there? That indicates that we missed the commutation point where it was supposed to be. The voltage waveform actually overshoots and then comes back down to the right level. And as you might expect, if the flux threshold is set too low, we get a situation where it looks something like this. By the way, don't worry about the glitches in the waveform. That's just a buffering issue between the processor and the PC. Here we go. Comes up, and then we actually jump up to the top waveform, which indicates that we're actually tuned too early. So what you want for optimum tuning is you want to have that rising edge of that back EMF waveform tuned so that it comes up just at the right time, and then instead of overshooting or jumping up, it just kind of immediately cuts over directly to the voltage the flat part of the voltage waveform. So when I tune it to about 4, now you can see it just kind of comes right up. Here's a good one. Yeah, it comes right up and then just goes straight over as shown there. So why is this? Let's take a look at some diagrams to see if we can understand better what's actually going on inside of the motor when this is occurring. So what we see here is just one phase of a 3-phase BLDC motor, which contains a 4-pole rotor. And what I'd like to do is to plot the flux linkage, which is threading through that coil of that phase as the rotor is spinning. And then also look at the derivative of the flux linkage, which will be the back EMF waveform, which is impressed across that coil. So I'm going to make an assumption that this particular motor has a sinusoidal back EMF waveform, which is not too outrageous of an assumption, since most BLDC motors do indeed have a waveform which at least resembles a sine wave for the back EMF. Now you notice right here, with the rotor in the position that it's currently in, I have an equal amount of south pole flux threading through this coil as I do north pole flux. So they kind of cancel each other out, and the net flux linkage at this particular angle of the rotor will be 0. But as the rotor starts spinning in the clockwise direction, more and more north pole flux starts cutting through this coil as shown here. So the flux linkage is actually going up until I get to this spot right here where the north pole is parked directly under this particular pole piece, and that will be the spot where I have the maximum flux linkage. However, the change in that flux linkage at that particular moment in time is 0, which is why the voltage right at that spot will be 0. But as I continue to rotate the motor for another 45 degrees, we see the north pole beginning to exit from underneath that particular stator pole piece, and more of the south pole starts to come into play until finally, once again, we have an equal amount of north pole flux and south pole flux, so the net flux linkage at that spot is 0. However, notice that at this point, the derivative or the change of the flux linkage is maximum, and that's why you have a very large back EMF at this particular moment in time. So let's go ahead and draw out the full sine wave, 360 degrees of this, so you can actually see what the whole thing looks like. And also remember that we're talking about just one phase of a three-phase BLDC motor. So since all of the phases are separated from each other spatially by 120 degrees, that means that each of the respective flux linkages will also be separated by 120 degrees, as well as the back EMF waveforms. Now let's go ahead and draw the commutation process on top of the back EMF waveforms. And you'll notice that if my motor does have a sinusoidal back EMF, I can have situations where the back EMF waveform will exceed my power supply voltage as shown here. Let's take a look at the green waveform. So here would be the case where the green waveform, I have the bottom transistor turned on, and also I'm going to superimpose the commutation intervals here. So right at this spot, right here, where the back EMF waveform for the green phase exactly equals the back EMF waveform for the red phase, that's where I would like to commutate my machine. So the bottom transistor for the green phase is turned on, and then right here I turn it off. During this particular interval, the green phase is tri-stated. So after the current has quenched in that coil, I actually now have visibility to the back EMF waveform. And then I wait until I get right here where the amplitude of the green phase, the back EMF waveform, equals the amplitude of the blue phase's back EMF waveform. And at that spot, that's where I want to commutate the machine and turn the green phase on. If I do that correctly, we should end up with a waveform that looks just like this, where you have a flat-topped bottom voltage, a kind of linear-looking ramp in the middle, where we're actually looking at the back EMF waveform, and then a flat-topped positive interval here. Now what happens if I commutate too early? Well, what that means is instead of waiting for the back EMF waveform voltage to rise to that commutation spot, we actually turn the top transistor on too early. So it yanks that green voltage up too early, and we end up with a waveform that looks like this. And of course, that's what we saw with the InstaSPIN-BLDC GUI. If we're commutating too early with a low flux threshold value, it created a waveform that looked like that. But what if we had too high of a flux threshold, which meant we're commutating too late? Well, then we actually stay on the green back EMF waveform longer than we should, and as a result it creates a waveform that looks like this. Finally the top transistor turns on and it does pull it down, and that results in the other waveform that we saw when we're commutating too late. So that's how we explain what the voltage waveforms look like when they're not commutated properly, and that's why it's very important to commutate the machine at exactly the right spot here. So go ahead and try to program the threshold correctly for the motor that you're using. Again, try to get that voltage ramp to come right up to the top and then just to flat top straight over without any undershoot or overshoot as shown in this waveform right here. If you're using the motor that comes in the 8312 kit, that's the Anaheim automation motor, we've noticed that setting the flux threshold to about 0.35, somewhere between there and 0.4, typically gives a pretty good performance for that particular motor. So again, what we're doing here is we're basically just pumping out a duty cycle, a PWM duty cycle to the motor based upon what I have my pot here programmed at. It's not in any kind of closed loop at all, so you can imagine that if I load the motor down, it's not going to regulate the speed very well. In fact, you can see from the speed graph there, the speed is going down. Also notice the horizontal meter underneath the main potentiometer. That is our current meter. So you can actually watch the current in the motor. As I load it, it actually increases there. So not very good speed performance at all. What do we do if we want to get better speed performance? We actually have several different operating modes here, and one of the operating modes that I want to talk about now is the velocity mode. So let me go ahead and put this in velocity mode. And when I do that, here's actually what I'm doing. I'm now putting the motor speed in a closed loop control system here to try to regulate it. So here's the commanded rotor speed. This is what's coming in from the pot, the main control pot, and I set that to a per unit value of, somewhere between 0 and 1. I then make a calculation inside the InstaSPIN-BLDC code of what the velocity should be based upon the commutation times that I'm measuring. I feed that velocity information back, compare it to the commanded rotor speed from the potentiometer, and subtract that from the commanded value to generate an error signal. The error signal is then split into two separate paths. One is a proportional gain path, and one is an integral gain path. And these two values right here in gray, these are the potentiometers that I will have the ability to adjust the gains of, so I can actually change the performance of my velocity loop here. So when you're tuning a velocity system, a velocity PI control system, how do you go about doing that? And quite honestly, a lot of it is rather empirical, but there is a method to the madness. And typically what you want to do is start off with very low values for both the P and the I gain. And the reason for that is, since this is a closed loop system, if you start having too high of a gain in your system, that means that your bandwidth response is going to go way out there in frequency, and you're probably going to find some poles in your system response that are hiding in the weeds that as soon as you get enough gain to pull them above 0 dB, they're going to start messing around with your phase margin, and then you've just built an oscillator. So the best way to start off tuning a PI control loop is to set those values as low as possible just to get the loop to function correctly, and then you can keep bringing them up to see what kind of performance that you get out of it. The P term typically sets the stiffness of your system across the entire bandwidth. So in terms of the how accurately the speed of the motor will track your commanded speed, you can adjust that with the P term. What does the I term do? Well, keep in mind this is in series with the integrator, so that means that it's actually amplifying the error signal to be integrated, and then it's combined with the P term to calculate the PWM value. The I term, when you set it to 0, means that the integrator is completely out of the loop, so you basically just have a P controller. But any non-zero value for your I term means that you now have activated the integrator. And having an integrator in your control loop means that the control system cannot tolerate any steady state error. It drives it nuts. Even just small steady state errors will eventually, they'll get integrated and integrated and integrated until finally you generate enough voltage on the output here to compensate the system to get rid of that steady state error. Now, how aggressively that it gets rid of the steady state error, that's what this I gain right here will determine. So for higher values of I, it will actually servo out the steady state error much faster. So let's return to our control GUI interface page right here. I'm going to go to the settings panel, and in velocity, for the velocity loop, only these two knobs right here are active. These right here are not active in the velocity mode. So I'm just looking at these particular knobs right here, and these are not the default values. These are values I've already set up ahead of time. I'm going to set the KP value to about 3, and I'm going to set the integrator gain value to about 20. And again, these are values that I determined a priori based upon experimenting with this motor. So now we're in velocity mode. Let me go back here and let's re-enable the motor. And that's because I have my velocity set too high. Let me go back and set this down to about 0.1. There we go. Now let's try it again. Let's enable the motor. Much better. So now let's go back to my main page and look at my graphs again. So you can see that it's, again, running at some velocity, but notice the difference now. When I try to load the motor down, the control system is going to fight me in an effort to try to regulate that motor speed. You can see my current going up, indicating that I'm actually putting a load on the motor, but you notice now that loaded or unloaded, it's fighting to try to keep that speed regulated at the same value, and I can't do that too much or else my hand gets hot from spinning the motor. Actually, quite amazing when you think about it. That little 8312 chip is driving that huge motor and generating enough power to actually get it so hot that I can't hold on to it when I'm trying to trying to slow it down. So anyway, that's the velocity control mode, and as the screen here indicates, for velocity control mode, it only controls velocity. There's really nothing to control the current. The current is completely out of control. Well, so what if we want to control the current in the motor? That's actually the next scenario that we'll look at. This is the current mode control topology, and in this case, we're doing the same thing for the motor current that we were doing for the velocity before. Here's our commanded current. Here's our bus current from the shunt resistor. We compare this to the commanded current, and again, run it through a PI control loop, and then we can actually feed that value then, add those two results together to create a PWM value to drive the motor with. So let me go back over to our control panel, our GUI interface. Right here we go, there we go. And let me stop the motor. And now I'm going to set it up to work in current mode. So let me find the values that I need to use for that. Let's go to the second page right here. Give me just a second here. Okay. Now I'm going to program this right here to a value of like 4.5. Get some really good gain out of this thing. There we go. And I'll put in a little bit of integration, maybe not quite that much, something like 5. Okay. And now we're going to put it over into current mode. And let's see what effect this has now. So if I go back to the main page, let's set it up to be something like, I don't know, let's try a value of 20. Now when I enable motor, let's watch what happens here. Okay, so it immediately tries to go to the fastest speed that it can go. Look at the velocity curve right here. Right here you can see, I mean, it just jumps to the fastest speed it can go because it's trying to command a lot of current. In other words, it's trying to control the torque on the motor. But since the motor has absolutely no load, it's just going to immediately ramp up to the fastest speed it can go, and then the system saturates, and then that's all the faster it can go. I can now easily load it down. Notice it doesn't try to regulate the speed at all. All it's doing is now giving me a constant torque. And I can prove that to you by lowering the commanded value of current. So let's go down to a value of, let's say 5 now on my potentiometer. Now what am I doing? I'm actually commanding less torque. So if it truly is controlling the current or the torque of the machine, it should take longer to ramp up now because I have to overcome the inertia of the machine with the constant torque that I'm applying. So let's watch this as we do this. Yep, and as you can see, it did take longer to ramp up to speed. Let's put it to a value of, I think this one's pretty interesting. Let's put it down to like 0.02. Watch this. Again, constant torque mode, but the torque I'm commanding is much smaller now, and as a result of that, it takes a much longer time to ramp up to speed to overcome the inertia of the machine. So that's current mode. Let me turn that off. So what do you do when you want to control both the velocity and the current of your motor at the same time? Well, that's a special mode on the InstaSPIN-BLDC GUI called the Cascade mode. And here's what Cascade mode actually looks like. You actually see that you have a velocity loop and a current loop which are cascaded together. That's how it gets its name. So the commutation engine is generating the commutation times. We do velocity calculations based upon those time intervals to provide an estimate of the rotor speed back to this comparator. The input to our velocity loop is the commanded rotor speed from the main control knob on the first page of the GUI. So we compare the rotor speed to the commanded speed to generate an error signal, and that goes through PI control loop for the velocity, just like we saw earlier with the velocity mode. The output of the velocity mode now, instead of driving the motor directly, it feeds into your current mode or your current loop. So if the velocity is too high, that means that I want to slow the motor down. It will generate a lower current for my current loop. Or conversely, if the motor is not going fast enough and I need to have more velocity, then it will increase the current commanded to the current loop. And this right here is where I can actually do the current control. The output of the velocity loop is clamped by the velocity loop limit. And this is where that is at. It's actually on the settings page, and it's this slider right here. I can specify exactly how much maximum current that I want the motor to be able to generate. So again, looking at this diagram right here, by clamping this, I now have control over the motor's torque and the motor's velocity. So I really get the best of both worlds in the cascaded mode. So let's go back here to the GUI interface, and I'm going to put it in cascade mode. And you'll also notice that I've got my KP and KI values already set correctly for this particular motor. Again, the way that I did this was to start off with very low gains, because with lower gains you're more likely to have a stable system. And then I kept increasing the gains until I got the stiffness in the system that I wanted. And again, I'm trying to keep the gain as high as possible without increasing my bandwidth to the point where all those undesirable poles out there at higher frequencies start causing a problem for my control loop. So I'm always kind of walking a tightrope here, trying to get high enough gains for good stiff response, but not so high that it's going to cause my system to oscillate. So let me go ahead and enable the motor now in cascade mode and go back to the main page, and we can actually see the velocity waveform here. Now notice as I load down the motor, once again it will try to fight me to maintain the velocity, but now I'm also controlling the maximum current that the motor can generate. And I can't do that too long because it really starts heating up pretty fast. So that is cascade mode. Again, it's used in situations where you want to control the velocity of your system, but you also want to limit the maximum amount of current that the motor can take. So let's review the control mode options once again that we have with InstaSPIN-BLDC. First of all, we have duty cycle mode, and all we're doing with that mode, it's an open loop control technique where I'm just pumping out a duty cycle to the motor, which is specified by the setting on my control knob here. We also have current control mode that actually controls the torque of the motor, but the velocity of the motor is not controlled. On the other hand, we have a velocity control mode, but the current is out of control. So you could easily overcurrent your motor with a velocity control mode. And then we have the combination of the two, which is the cascade control mode. This is a velocity control loop, but it also has an inner current loop, so you can actually control the current as well. Now, in some cases, your motor may not start up correctly, even if the flux threshold is properly tuned. And that brings us to some of the more advanced features of InstaSPIN-BLDC. And I want to call your attention to the startup control panel over here. Now this actually controls the open loop starting technique of the motor. Since InstaSPIN-BLDC is based upon back EMF readings, we have to somehow start the motor open loop to get the motor spinning so that we can get some back EMF readings off of it. And in the startup control panel, you have the ability to control the duty cycle of the startup waveforms, and you also have the ability to control the ramp time of the startup waveform. And this can prevent fault tripping with high load inertias. Let's say that I had set it to something like 800 milliseconds. What that means is that it will start rotating the motor at a speed which is specified by the start speed, RPM, and then 800 milliseconds later it would have ramped up to the end speed that you program in right here. So it gives you quite a bit of flexibility in terms of dealing with motors that have different inertias and things like that. We also have an advanced startup system here, and this is actually a recent enhancement to this technique, which is rather intriguing. It kind of works like the starter motor on your car. So when you get into your car and you turn over the key, you can hear the starter motor turning over your main engine. And you don't let up on the starter motor until you finally hear the combustion engine kick in. And that's kind of the way that this works too. It overrides the startup ramp time altogether and says just keep doing the startup indefinitely until you get conditions that match the parameters that you specify in these two boxes right here. So when you first start up, you have an open loop algorithm which is just banging out commutations to the motor at a specified interval. And you also have your back EMF observer which is running and trying to predict where the commutations should occur. So what you do is you compare the actual commutation events against those predicted by the InstaSPIN-BLDC algorithm, and you can program in what the error has to be between those values before you're willing to release control over to the closed loop algorithm. And you can specify how many consecutive commutations that have to match this time parameter right here before you're willing to let go. So let's watch how this thing works right here. I'm going to start it up. Let me click Enable Motor. Now it's trying to start the motor, and it can't get any commutations that fall within this error band. So I can just kind of change this until finally I get an acceptable error band, and then all of a sudden it says, okay, you've had 3 consecutive commutations that met this particular error time right here, and then it transferred over to the InstaSPIN back EMF integration technique. A couple of other slides, or a couple of other screens that I want to show you just in closing. We also have the D3 engineering slide, and this is just kind of a reference page which has their website. You can actually link to it, get more information about what D3 does. They're actually one of our better consultants that helps us out with projects like this. Very focused on motor control, as you can see here. So if you're looking for some consulting help that involves motor control, consider using D3. And then also we have the crosshairs embedded interface. That's what this whole project is built upon. And you can also get more information about that, how to do your own crosshairs GUI interface if you want to, or just more information about their products as well. So again, this is InstaSPIN-BLDC, and it actually works very well on a multitude of different motors. We've tried this technique out on literally, I'm guessing, maybe 80 to 100 motors now. And in each case, with this interface, we were able to get the motor up and running, usually within 5 to 10 seconds, and suitably tuned with the flux threshold in under a minute or two. So it's a very, very adaptable technique, very insensitive to your motor parameters, and it will learn your system very, very quickly, and you'll have your motor up and running in a very small period of time. So thank you very much for your attention. And again, if you have any questions about this, please contact somebody at TI. We'd be glad to help you get your system up and running using InstaSPIN-BLDC.